The VHF omnidirectional range, VOR, was adopted as the standard short-range navigation aid up to 200 nautical miles in 1960 by ICAO. On the left, we see the first generation of transmitter, and on the right, the second generation Doppler equipment. The VOR produces 360 radials at 1 degree spacing, which are aligned to magnetic north at the VOR location. The equipment in the aircraft indicates which radial the aircraft is on, and whether it is flying to or from the VOR. It is practically free from static interference, and it is not affected by sky waves, which enables it to be used day and night, unlike ADF. When the VOR frequency is paired with co-located distance measuring equipment, DME, an instantaneous range and bearing fix can be obtained. VORs have several uses. They mark the beginning, the end, and centerline of airways, and these are called en route VORs. They are used for navigating to airfields, and as a letdown aid at airfields using published procedures. They are used as part of a holding procedure, and they are a source of en route navigation position lines and crosscuts. All VOR ground stations, except test VORs, perform the same basic position function, but there are variations on the theme, such as the BVOR. This is a broadcast VOR, which gives weather and airfield information between beacon identification. TVOR stands for Terminal VOR, which operates on low power and is used at major airfields for location and letdown procedures. En route VORs form part of long-distance navigation routes. VOT is a test VOR, which provides no navigation information. It broadcasts a fixed omnidirectional signal which shows that the aircraft is always on the 360-degree radial. Aircraft equipment should be accurate to within plus or minus 4 degrees. VORTAC is a military VOR, which has co-located distance measuring equipment, TACAN. Only the DME function is available to civilians. DVOR, or Doppler VOR, eliminates some conventional VOR problems. We will look at this in more detail later in the lesson. VOR equipment and instrument landing equipment share the frequency range from 108.0 to 117.95 MHz and have a horizontal polarization. Frequencies in this range with an odd first digit after the decimal point are allocated to instrument landing equipment. Thus, 108.10 and 111.95 are ILS frequencies. Frequencies with even numbers after the decimal point are VOR frequencies, such as 108.0, 108.60, and 111.80. The emission characteristics of VORs are A9W. The letter A stands for main carrier amplitude modulated double sideband. The number 9 stands for a composite system, and W stands for a combination of telemetry and telegraphy. Telemetry is the transmission of measured quantities, in this case, phase difference. The VOR usually has a 3-letter Morse identifier, or ident, which must be checked before it is used for navigation. The identifier is transmitted at least 7 times a minute, and may be either in Morse on its own or preceded by a voice description, such as, "This is Miami Omni." The voice channel of the transmission may also be used to carry airport information via ATIS, the Automatic Terminal Information System, when there is no discrete frequency for the ATIS. This is a BVOR. If a continuous tone or a series of Morse dots is heard, this indicates a test VOR. That is, it gives no navigation information, but it enables a pilot to check whether or not his display is accurate. This is for ground use only. All VORs are monitored by an automatic site monitor, which will warn the control center if there is an error of greater than 1 degree, there is a reduction in transmitter power of greater than 15%, or the monitor itself fails. To warn the pilot that bearing information is unreliable, the Morse ident is suppressed until the standby transmitter is brought online, which usually takes a few minutes. A red or a yellow and black warning flag will also appear on some aircraft indicators. VOR bearing is obtained by phase comparison. An aircraft's VOR receiver measures the phase difference, that is the angular difference, between two signals from the VOR transmitter. Think of a lighthouse and imagine the whole light rotating at a speed of 1 revolution every 60 seconds. Wherever you are, you will only see the light once every minute, and people in different places around the lighthouse will see the white light at different times. Every time this white light passes through magnetic north, a green omnidirectional light flashes, which is seen by everybody, wherever they are, at the same time. The white light rotation speed of 1 RPM equates to 6 degrees per second. So by measuring the time between the green flash and the white flash, you can tell your position in relation to the lighthouse. If you see the white light 30 seconds after you saw the green light, you are on the 180-degree radial from the lighthouse, due south. Let us call the green light the reference signal, and the white light the variable signal, and see how this now applies to the VOR. The ground station emits two signals. The reference signal is an omnidirectional continuous wave transmission on the carrier wave of that particular VOR station that is frequency modulated at 30 Hz. In the aircraft, it is this part of the signal that is used as a reference for measuring phase difference. Since this is an omnidirectional transmission, the polar diagram of the reference signal is a circle. The second signal, the variable signal, is effectively an electronic loop aerial, which produces a figure-of-8 polar diagram, as we saw in the NDB ADF lesson. It is electronically rotated at 30 revolutions per second. When the two signals are mixed, the resulting polar diagram is a limison. Unlike the cardioid of the ADF, it does not have null positions. The limison itself is rotated at the rate of 30 revolutions per second, and this has the effect of amplitude modulating the carrier wave. This means that the signal is received at different strengths in the aircraft. Each receiver is now receiving both a reference and a variphase signal, and the rotation of the limison is so arranged that the two signals are in phase on a magnetic bearing of 360 degrees from the VOR beacon. This is like our green and white lights at 360 degrees. By comparing the constant reference signal with the changing strength variphase signal, it is possible to determine the aircraft's bearing to the VOR. The first generation of VOR, suffers from reflections from buildings and terrain in the vicinity of the VOR, so that two signals reach the aircraft out of phase. Instead of a straight line signal, it has bumps or scallops in it, which cause the CDI to waver from the centre. Propagation errors, known as scalloping, may also occur at extreme range and at low altitude, where the signal is unevenly propagated over irregular terrain. These errors are cured by using Doppler VOR, which has a wide-based antenna array, 13.4 meters wide, and usually with 48 transmitters in a circle. It also uses the Doppler principle of frequency change with distance. The variable phase signal is frequency modulated in the Doppler VOR, whereas it is the reference signal which is frequency modulated in the older VOR system. Frequency modulated waves are subject to less interference and are therefore more accurate. The Doppler effect is created by electronically rotating anti-clockwise the variphase signal on the circular aerials at a speed of 30 revolutions per second, which equates to 1,264 meters per second. This is fast enough to create a Doppler shift, as the signal increases in frequency as it approaches, and then decreases as it goes away from the aircraft. This shift is then measured. The aircraft equipment does not know whether the signal is from a conventional or a Doppler VOR. We have looked at the ground equipment. Now let's look at the aircraft equipment. The antenna, which is a horizontally polarized dipole, can take one of several forms, depending upon the age of the aircraft. Older aircraft have large dipoles, whereas new aircraft have smaller blade-like antennae. A receiver is tuned to the appropriate VOR frequency, and the signal from the antenna is sent to the receiver. This is then interpreted and displayed as a narrow needle on its own display, a coarse deviation indicator, the CDI. It may also be